Hello everyone. Today we are going to introduce a basic knowledge of serial communication. When talking about serial communication, you must have the concept of UART and serial interface. This will definitely help you a lot in solving serial communication problems. The most important part today will be UART and serial interfaces, including RS-232, 422, and 485. The course outline will be UART introduction and serial interface introduction. In the block diagram, we can see what we need to perform a communication. It includes CPU, software, and hardware. Today I will focus on the hardware part, which includes UART and EIA driver. An EIA driver is also called a transceiver. Okay, now let's get started from UART. UART, Universal Asynchronous Receiver Transmitter. It translates data between parallel and serial forms. We can see in the yellow area is an example showing how data goes in parallel way. The 1 byte, which is 8 bits, go from the left side at the same time and arrive at the right side at the same time. That is called parallel. On the other hand, serial is a way that data passes through by making a line. You can see in the blue area. In serial communication, data goes by making a line, 1 bit by 1 bit, and UART is the translator in between. In this figure, you can see the 4 parts in UART: baud rate generation, transmit FIFO, receive FIFO, and modem control. I will introduce these 4 parts in order. Before jumping in UART's main function, let's take a look at serial data format first. For serial data, it includes start bit, data bit, parity bit, and stop bit. Start bit is always set low, 1 bit. Data bit can be set from 5 to 8 bits. Parity bit is 1 bit. It is used for checking if the data is correct. Stop bit can be set 1, 1.5, or 2 bits. You might wonder what parameters should be set. Don't worry. Usually the parameters are predefined on customers' devices. All you have to do is to set the parameters same as those devices. Baud rate. In serial communication, it is usually defined as bits per second. It means how many bits can be transmitted per second. For Moxa product, the range is from 50 to 921.6 kilobits per second. Next is FIFO, first in, first out. We can think of it as a buffer. It is designed to improve communication performance. It depends on customer's application to set up our FIFO. If customer needs high throughput, we can enable FIFO. If he wants small latency, we can disable FIFO to force UART to transmit as soon as it gets the data. At transmit side, let's assume the FIFO size is 64 bytes. When the FIFO is empty, UART will send interrupt to CPU. Then CPU will write length 64 bytes data to UART in one time. But if there's no FIFO, whenever UART transmit 1 byte, it will send interrupt to X CPU to provide a 1 byte data. Obviously, under the situation, the CPU loading will be heavier. For the receive FIFO, there are 2 situations that UART will send interrupt to CPU. One is that data in UART is over 32 bytes. The other is that receive timeout happened. Each one of the situations happens, it will trigger CPU to read the data in UART. There's one thing I would like to deliver. In order to prevent data loss and improve performance, FIFO can use RBH, which is Receive Buffer High Water Level, and RBL, which is Receive Buffer Low Water Level, with flow control to achieve it. If the data size is over RBH, receiver will use some way to inform the transmit FIFO to stop transmitting data. If the data size is less than RBL, receiver will use some way to inform the transmit FIFO to start transmitting data. Flow control is the way to prevent data loss and improve performance, which works with RBH and RBL as we mentioned before. There are hardware flow control and software flow control. Hardware flow control uses RTS, CTS, or DTR, DSR control signals. Software flow control use certain characters. If there is no control signal, the only way would be software flow control. For hardware flow control, if the data size in receive FIFO is over RBH, receiver sets its RTS to low, and the CTS at transmitter side will be low at once. So the transmitter will stop transmitting data. If the data size in receive FIFO is less than RBL, receiver will set RTS high to inform transmitter to start transmitting data. For software flow control, if the data in receive FIFO is over RBH, receiver will send a word X off to ask transmitter stop transmitting data. If the data size in receive FIFO is less than RBL, receiver will send X on to inform transmitter to start transmitting data. I believe you have already known UART very well. Now let's start the second part, Serial Interface Introduction. In the following slides, I will introduce RS-232, 422, and 485 to you. This table is the comparison of different interfaces. RS-232 is full duplex. Distance is 15 meters at 9600 bits per second. It has control signals RTS, CTS, DTR, DSR, and DCD. The topology is only point-to-point. RS-422 is full duplex. Distance is 1.2 km at 9600 bits per second. The topology is usually point-to-point. RS-485 is half duplex. Distance is 1.2 km at 9600 bits per second. The topology is multi-drop. Now I'm going to show you more detail about RS-232. This is a table of RS-232 signal definition. Let's look at the data signal column. For transmitter, 5V to 15V will be a logic 0. Minus 5V to minus 15V will be a logic 1. For receiver, 3V to 25V will be a logic 0. Minus 3V to minus 25V will be a logic 1. Minus 3V to 3V will be an invalid signal. For control signal, it's the opposite. Minus volt is logic 0. Plus volt is logic 1. This table shows RS-232 pin definition. TXD is for transmit data. RXD is for receive data. RTS, CTS, and DTR, DSR are used for flow control. GND is ground pin. RI is not used currently. There are DTE and DCE in serial communication. DTE is data terminal equipment, for example, computers. DCE is data circuit terminating equipment, for example, modem. This is how PC and serial device be connected together with a straight cable originally. But today, as modems are not popular anymore, we rarely see this application. This is a more modern way to use serial communication. Since two sides are DTE, we need to cross-connect the pins. As you can see, the DSR pin is short with DCD. This is to ensure all types of software can work, such as serial console port on rack server. This is a simple way to use RS-232. It uses only transmit, receive, and ground pins. Now, let's move to RS-422 and RS-485. RS-422 and 485 uses differential signal. It is also named balanced signal. If one wire is transmitting a high, the other wire will be transmitting a low. The pair is twisted and equal length. The benefit of differential signal would be low voltage, long distance, and high noise immunity. This is the signal definition of RS-422 and 485. They are only data signals. For transmitter, -2V to -6V will be a logic 0. 2V to 6V will be a logic 1. For receiver, -0.2V to -6V will be a logic 0. 0.2V to 6V will be a logic 1. And the signal between 0.2V and -0.2V will be invalid. In this page, it shows RS-422 4-wire connection for point-to-point. This is a RS-485 2-wire connection way for multi-drop topology. We can assume MSB card as a master, PLC devices as slaves. The whole behavior is one request, one response. It means master will send a request to one of the PLCs to ask for data. Once PLC gets the request, and then it will send the data back to the master. There is one thing I would like to highlight in this page. You can see there are 120 ohm set on both end sides. It is called terminator to prevent signal reflection. In order to work on bidirectional data transmission in two-wire mode, RS-485 has tri-state status, also known as floating, high Z signal, high impedance mode. But how to work? One is RTS control. This is an internal circuit uses RTS status to enable or disable. Set RTS low when no data be transferred. Set RTS high when there's data to be transferred. But RTS status is controlled by user's software, so it is not so efficient. The other is a Mozart patent technology named Auto Data Direction Control, ADDC. In ADDC, hardware will control the data direction automatically. When there's transmit data detected, hardware logic enables the RS-485 transmitter until data sent. And when there is no transmit data, device go back to listen mode. This is another application of RS-485, the 4-wire connection. It's multi-drop and full duplex. There are 4 main functions of UART I hope you can remember: baud rate generation, transmit FIFO, receive FIFO, and modem control. Let's take a look at this table again. All the information in this table is very important. I hope you can remember them as much as you can. Thank you for your listening. Don't forget to take the quiz to see how much you have learned.